Welcome to this lesson on hybrid orbitals. In this lesson, we'll talk about how hybrid orbitals allow us to predict the geometries and overall shapes of the compounds that we're looking at. Hybrid orbitals allow us to visualize what the electrons are doing and what shapes they're making around the compounds when they're forming a bond. So to describe this, we're going to take a look at this simple compound called beryllium fluoride. I've drawn the Lewis structure there, and it shows the bond between them. We expect this compound to be linear, but let's try and look at it in terms of its molecular orbitals. So to start this problem, we're going to take a look at the electron configuration for each of the atoms. If we look at beryllium, we understand that in the valence shell, this has a 2s, and then there's also a 2p. So we draw out the orbitals as shown here, and now what we do is we place the electrons into them. So for beryllium, there's 2 valence electrons in its outermost ring. So this is what it looks like. And so as you can see, those electrons are actually paired up. This is problematic for us because we want to be able to form a bond. In order for us to form a bond, we need our electrons to be unpaired. So what we do is we draw it a different way. So we have the 2s and we have the 2p. So we have 3 empty p orbitals here. So what we can do is we can move one of our electrons from the 2s to the 2p. So now we have 2 available electrons available for bonding. Now if we take a look at fluorine, we have a 2s, we have a 2p, 2, 3. So this is what the configuration for fluorine looks like. And you can see fluorine has 1 unpaired electron available for bonding. That's why you typically only see fluorine bonded to one thing, because there's only 1 unpaired electron. So now let's look at beryllium one more time. So we want to see how these orbitals are going to hybridize, meaning how they're going to pair together to form a new shape. So if you look at the 2s, we draw it out. We have this as the 2s, and then we draw out one of the p's. Let's call this the p. What we're going to do when we're hybridizing, we're adding the 2 orbitals together, meaning they're going to form a new shape. So when we're adding 2 orbitals together, we're always going to end up with 2 in the end. So what we end up getting when we add them up is we get a shape that looks something like this, and then another shape that looks something like this. So those drawn separately, we can also draw them together, and we end up with this shape right here. So this is what we call the sp hybrid orbital. So if you take a look at that shape, you can easily see that in order for another orbital to interact with it, it needs to be in a linear fashion. So if I take this sp hybridized orbital for beryllium, and then I take over here for the fluorine, it has a p. So now what we can do is we can have interaction between the fluorine's p orbital and then the sp orbital of beryllium. So you can see we have overlap here, and we're able to form a chemical bond. So that's why when you have sp hybridization, you always get a linear shape. Now let's look at a different case. Let's look at a sp2 hybridized orbital. So an sp2 hybridized orbital is going to be something that has an s and a p orbital and another p. So if we just draw that out, we have an s, we can draw a p here, and then we can draw another shape for the p. So remember there's 3 p orbitals. We have the px, the py, and the pz. In this case, we'll just be drawing the px and the py. So if we add all of these orbitals together, we end up with a hybridized structure. So remember, we have 3 orbitals that we start with. When they hybridize, they have to have 3 in the end. So 3 different shapes we're going to get. Now if we take these orbitals, we add them up together and we show it all in one piece, we're going to end up with the structure that we expect for something that's a trigonal planar. This is what you end up getting, and you'll notice things that are sp2 hybridized are always planar, meaning that they're flat. So now let's talk about sp3 hybridization. sp3 hybridization is just like sp2, except we add an additional p orbital to the mixture. So to explain this, we'll take a look at CH4, methane. So when we draw the electron configuration for methane, we have a 2s and a 2p. Typically draw it out like this. So you can see this isn't possible for us to form 4 bonds the way that we've drawn it here. So we need to take those electrons from the 2s and we need to move one of them into the 2p. So what we end up getting is a configuration that looks like this. And from this, you can see that we have 4 unpaired electrons that allow us to form 4 bonds. And so for sp3 hybridized, what we end up doing is we end up forming, we have an S, we have a P, have another P, and we have this one. So we got our PX, PY, and our PZ. So in this case, we have 4 orbitals. We're going to add each of these up together. And remember, when we add these up, we should end up with 4 in the end. And so this one's going to be a little bit hard to draw, but we should end up with something like this. When we add that all up together, you'll notice that this gives us something that looks very similar to the shape for a tetrahedral geometry. So for sp3 hybridized, we can have 4 different domains around it to give us the tetrahedral geometry. Now let's do an example where we talk about how we can determine what hybridization this compound has. So this is ammonium ion. So you can see if we draw out the Lewis structure of it, it has 4 different things attached to it. It has a nitrogen with 4 hydrogens. So what we want to do is we want to look at the amount of domains around it. So domains, we call them things that are attached to it. So in this case, a hydrogen. And then also we look for lone pairs. In this case, there's no lone pairs and there's just 4 things around it. So it has 4 domains. Now what we can do is we can look at the shape of it. So we should understand that this compound has a tetrahedral geometry. Then what we want to do is we want to look at the hybrid structures here on the right. So the different shapes that are allotted for each of the hybridizations should determine which hybridization the nitrogen has. In this case, we know it's a tetrahedral geometry, so we can look at each of the hybridizations. So the sp, we know that's going to form linear structure. So it can't be that. Then if we look at the sp2, we know that forms trigonal planar structure. So we know that doesn't match up. It also doesn't have enough bonding areas available to form 4 different bonds. So we know that can't be it. Then we look at the sp3. We know that the sp3 adopts the tetrahedral-like geometry. So we know that this compound would end up being sp3. Then what we can do is we can look at a different compound. So if we look at SO3, so SO3, if we draw the Lewis structure for it, it's going to look something like this. So SO3, you can see there's 3 things attached to it. There's no lone pairs, and this should adopt the trigonal planar structure. So we know it can't be sp, and we know it can't be sp3. So it has to be sp2 hybridization. We can also look at this in another case. So if we look at the compound CH2O, we draw out the Lewis structure for this compound, we end up getting this. This compound we know has three things attached to it. It adopts a trigonal planar structure. So we know that this is going to have to be sp2 hybridization. We look at another compound, H2CCH2. We draw out the Lewis structure for this compound. We get this here. So if we want to find the hybridization of the carbon, in this case, there's three things attached to each carbon. So we can say that these are going to be sp2 hybridized for each of them. Thanks for joining. If you have any questions, post them in the comment section below.